just going to put a timer on, otherwise I could talk for more time than I'm supposed to talk for. So yeah, I'm going to present to you how the HotSpot and Graal JVMs execute Java code. Okay, that's a talk I'm doing at KubeCon next week, and just for background, last week I was talking to the KubeCon program committee, and they said, "Are you going to practice your talk?" And I said, "Oh, yeah, that sounds like a great idea." And they said, "Oh, well, Frank, who runs the New York Java user group, he kind of might be able to do a review for you." So, okay, well, I could also just come here and present to more people. That'd be really cool. And just, this community is awesome. Like the amount of time and effort that's gone into turning this around within a week has just been amazing. And thank you all for coming at short notice as well. It's really appreciated. So thanks for that great introduction. I did write this book with Ben Evans called Optimizing Java, which is a little bit before Gough came out. I also had a really good talk here. I think I was trying to remember how long ago it was. It might be over 5 years ago with Ben Evans on some sort of micro benchmarking. I work at Morgan Stanley. It's my day job. Sort of basically working on API gateways and sort of Java programming there. That's one of the reasons why we're in town. We've been at the O'Reilly Software Architecture Conference at the beginning of the week. And I also do quite a bit of hacking around with Maven. For those of you that probably most of you use Maven as part of your build system. The maintenance on Maven is done by between 5 and 10 people that it's not their day job. So I've been helping them with some projects, and I'll sort of talk about one of the cool projects that I'm working on as we get through this talk. So here's a picture that I'm going to put up, and this is basically, rather than having a content to my talk, this is the area that I want us to explore as we go through the session. So this is something that I've been working on for, I want to say since I started working on Optimizing Java, the book, trying to fill in this picture of what's actually going on when you hit run, and your application just fires up and does all the good things that you're doing every day. And one of the nice things about Java is that you don't need to know what's going on behind the scenes. It's one of those things, when we moved from C++ to Java programming in general, you didn't have to have those complexities of memory management and sort of like all the details that you have to go into. Now, trade-offs, of course. Like sometimes you want those things, sometimes you don't. And we'll talk about how the JVM has sort of evolved over the last 25 years into what it is now. So the part that you're probably most familiar with is writing Java source code and running a command called JavaSIG to actually run the compilation into class files. Now, a lot of this, again, as I was saying, it gets hidden behind your build system. So you don't necessarily see what JavaSIG is doing. But actually, it's fairly lightweight. So as we go through, we're going to inspect what actually happens within the class file. But in order to sort of know the layout of the class file and what's actually in there, there's kind of like this layout that each class file has. The top is the magic number, which kind of describes that this is a Java file that you're looking at. Probably one that people are running into more and more now is the version of the class file format. So previously, Java only changed every 5-6 years, and you wouldn't kind of see this like the incompatibility with class formats so often. But if you try and run something, for example, with Java 11 that you compile with Java 13, you'll sometimes see this incompatible major and minor number error. And that's because you've got this checking this the class file format. You've then got in there things like the constants that are inside the class itself, the access flags, so whether something's abstract or static, and then other things that are to do with like your inheritance hierarchy, so the this and superclasses, and any interfaces that the class actually corresponds to, and then the actual methods and the code that's within those methods and the corresponding attributes. So obviously, this kind of thing, you need a good acronym to remember this by. So the acronym that I use is My Very Cute Animals Turn Savage in Full Moon Areas. So that's, if you ever need to remember that, if there's ever a quiz, if you ever go to a Java quiz, that's something for you to remember this by. So in terms of like the type descriptors then, this is something that we're going to see using a tool called Java P. So if you've seen JavaSIG, that kind of does the compilation. What Java P allows you to do is to look at the actual class file itself. So you can actually inspect what's there. And the output of Java P is a little bit strange when you look at it for the first time. So there's some examples I've got here just to kind of like give you a bit of an introduction. So this top one here is a method that returns a string. The middle one is a method that takes an int but doesn't return anything because it's void. And then the last one is a method that takes a string and an int and returns a log. So there's kind of interesting things in here. There's all of like the primitives, and then mostly reference types that we would use within our Java applications, probably the most. So here's a simple example that we're going to use throughout this actual talk. It's not particularly complicated. It's just a slight modification of hello world. So in my hello world class, I have a main method, and I have an iteration of 1,000,000 times, and I'm printing an int, which is a function, which I'm going to call with the current integer. And then down in here, I'm going to do system.error.println, and I'm going to do hello world plus a number. So it sounds really weird. Why would you be doing that, Jim? That just sounds like you like saying hello a lot. But what we'll see is as we go through like the actual application and go through this session, that will trigger various different optimizations that we can then look at and sort of explore a little bit further. So although it seems like weird, there is a method in the madness. So what we can do then is we compile our JavaC into our class file. We use something called JavaP, and we can inspect the bytecode. And after my very brief introduction, you're all now bytecode experts, of course. So the first thing that you'll notice is that hello world has been given a constructor, even though it hadn't defined one. So that's one of the rules in Java. If you don't have a default constructor, Java will give you one, essentially. And you can see in here there's a special type of invoke special, which is reserved for sort of basically initializing your object, and you can see that that's calling object init. You've then got your main method, and your main method there is doing a whole bunch of things. So it's doing it's loading in the variables that are around the loop. It's got the if compare greater than equal to in there as well, and it's invoking the static function printing, and then it's doing the increment and the goto. So obviously we don't do gotos anymore, but they're still there. They're just hidden away from us behind the scenes. Okay, so the print-int then, this is where it kind of gets really interesting. This is one of my favorite parts about like JavaC, because it doesn't really do very much actually. Its main thing is to take your Java code and convert it into bytecode. It doesn't really do many optimizations along the way. However, here you can see that what we've got is inside printing, we get hold of the print stream, that's the thing behind println essentially, and then we do this invoke dynamic. Okay, so this is kind of like one of those defer the invoke until runtime. And for those of you that are familiar with Java, this is kind of like the basis of what lambda expressions do. So that's essentially was introduced into the language for the dynamic system. And then we go and invoke the print stream with the corresponding make concat with constants. Okay, so that's what's going on behind the scenes. But what I find really curious about that is essentially Java 9, right, and beyond. If you go back to Java 8, you've got this idea of, well, the bytecode looks completely different, because there was no invoke dynamic. Or there was, but it wasn't used as much. So the idea here is that you've got print stream, and then you've got the string builder that comes in behind the scenes, right? So you created a string builder, and now you're invoking string builder initialize, and you're doing the concatenation with the string builder. So here's a curious thing. How many of you have been through a code review where somebody has said, don't use that string append, use a string builder? Right? Because you're going around in a loop, so it makes more sense to use a string builder. Well, kind of interestingly, that's changed. So you don't know whether something you did in 8 is still as performant as what it would be now in 9 and above. And that's also an interesting thing where code reviews and how you view Java from before is potentially quite different in terms of how it executes today. So it's just a funny one, if you enjoy looking at bytecode. So we have our class file. And this is all done ahead of time. That's where you run your Maven build or whatever else you've done. And we need to get that into the JVM in some way. So this is where the class loader comes in. So the class loader is all about how do I take my class file that's represented in just a file on the file system and load it into what I would call a method cache. Okay? So what actually happens? Now, this is kind of interesting because class loaders are, I think they really prove how dynamic the JVM is. And kind of, if you think about how class loaders work, you don't know what class you're about to use until just before you use it. And that's when the class loader kicks in and pulls the class in that it needs. Now, you probably haven't seen this for a long time because build systems have gone, they're really, really good. So you get that same class path at build time and runtime. That's something that's almost been hidden away from us. But some of you may remember getting things like class not found exceptions, or no class defined found error. So you can run into different types of error that are basically a result of trying to load the class just before it's needed. So the class file is loaded into something called the class object, and that's the mechanism for representing classes in the VM. So what I'm going to do, just to prove this to you, is I'm going to show you a little demo, which is one of my first demos, so hopefully this one goes well, so I'm confident about the next demos as we go along. So this demo is something called the watching class loader. I've been using this as when we were saying I was a teacher before, I use this tool to kind of prove how dynamic the class loader is. So what I've done is I've implemented my own class loader here. Okay? So it does a bunch of things. I'm not going to walk through the code in super detail, and excuse the fact there's no comments and probably bad programming standards in here. It's just a demo, right? So what I've got is I create my watching class loader, and I register against the file system a watch. So using the file.nio libraries, I'm watching a folder for basically something to drop in. Now behind the scenes, I've got something called compiled Java code. So inside it, from Java 5, actually there was a really interesting plugin that was added where you can compile Java code with Java. So you can basically run JavaC from within a running Java process. And then I actually load the class in, which is the overridden method, and I do kind of basically go and have a look and see if I can resolve the file. So the run is just using something really nice and magical called reflection, so I can have a look and inspect what classes are loaded. So if we start this up and this demo is playing nicely, oh, that's a little bit small, but I'll kind of walk you through what it's doing. So it's beginning the watcher, and if I type in demo, I'm going to get this painful class not found exception because it doesn't exist yet. It's not on my class path, I've not loaded it in. So what I'm going to do is I have over here demo, which is just a Java class file that's got a getA that returns 42 and a setA that basically does nothing. So what I'll do is I'll copy this file into classes. And what you can see down here is it's saying, oh, I've attempted to load demo.java and I've attempted to load java.lang.object. So you hadn't loaded that before, so that gets deferred up to the parent class loader. And what I can do here now is if I type in demo, you can see that the class is now loaded into basically into the running JVM. So this is kind of curious. Like that's the dynamic nature of the class loader. Normally you're sourcing from the class path, but you can write one of these that do anything. Like basically, I've seen all kinds of curious class loaders that do things like there's a custom class loader that goes off to some network location and loads in something that you've had to pay a license fee to use. It just makes things incredibly slow. And then you'll see people do tricks like do class.forename at the beginning, which enforces that the JVM loads the class. We used to use that in some of the stuff that I worked on just to try and avoid class.found exceptions catching people out later on. So yeah, that's something that's kind of fun to play around with. And there's a lot of different things in there that I used to use to teach Java. Okay, so that's class loaders. We've got into our JVM the class that's represented, and now we're going to do interpreting. Okay. This is often where Java gets its reputation for being slow, right? And we all have colleagues that work in C++, I would imagine, or in an alternative language that would say, well, Java's pretty slow, and that was true at the beginning, because the story ended here. Like the interpreting story was really the end of what went on. There's probably, of all the interpreted languages that we have now, most of them are not genuine interpreters anymore. Most of them do some kind of compilation and leave the compile file around. Python does the same. Java does something interesting with leaving compile files around in that it doesn't. And we'll talk about why it doesn't do that as we get through this talk. So interpreting is where we're going to basically go through the stack machine that the JVM has and take a group of bytecode instructions, match them to a template, and then execute them at runtime. So it's going to basically build the machine code representing your instructions on the fly. So initially, everything is fully interpreted, and there's a conversion of general instructions, not strictly speaking each instruction, and you can change that slide, to the corresponding machine instructions. Okay? Now this is kind of interesting because it's not wasteful. Like Java doesn't spend time compiling things that are only used once. And if you think about the startup of something like a traditional Spring application, a lot of things that are done at the beginning are things like reflection, and they're looking at kind of like the context that you're wiring together. sort of looking at those and compiling them might be wasteful in terms of time. So the idea is that the JVM waits until it's got this picture or this profile of how things are actually being used within your application. So you do get like a real advantage having this like actually being inside of runtime. And that's like kind of where some of the stuff starts to get quite interesting from the story that we're essentially building up. So what does the JIT compiler do? So this is actually the part where things get interesting from the perspective of this talk. Because all that other stuff has been around for a while, and the JIT compiler in terms of HotSpot has also been around for a while. So it does a couple of things. It looks at the profiling information that's occurred whilst your application's been running. Now this profile isn't particularly complicated. It's just basically counters. And it's showing that, okay, well, when you went into main, you were executing print in, and then that executed print line, as an example. It's just counting those invocations. And at a certain threshold, it triggers the compilation process. So all of the compilation that you do is based on the heuristics that you've got from the current run of the application. So I'm going to use this example, which I've used once before and it caught me out, but I'll use it again. If you imagine a site like Ticketmaster, imagine it's still built on a monolithic architecture. So if you imagine Ticketmaster, when you're selling tickets, your application is going to probably work in a way where people are going in, entering their credit card details, buying the tickets, and then they're logging out. That would be probably the profile of the application, generally speaking. Imagine then the next day when somebody's trying to, regrettably unpurchase all those Beyonce tickets that they bought the day before. Like when they're doing that, the profile of the application will be different. But the JVM would optimize based on those two different usage scenarios, and potentially if it was the same application running from the day before, it would reverse its optimization decisions that it made yesterday. So it's very dynamic in the way it can back out of its decisions. I always like that kind of idea that it can make a decision, then it's wrong, it'll just back out of it and just go back to interpreting for a while. So this is actually really quite cool, and you then effectively get this step of compilation. We're going to go into that in some reasonable detail. So Java observes that code using basically profile data. It's quite lightweight, and that triggers the compilation. It uses that profile to make informed optimizations, and we're going to look at the different optimizations that happen. Now the class loader means that the JVM doesn't know what's going to happen and when, right? Because you could all of a sudden load in a new class that changes something in terms of the structure of the objects that you have. And that can kind of lead it to having to do some backouts of decisions it's made in the past. So that is then, the idea is that we're then creating this really accurate machine code that represents what our application is effectively trying to do at that time, and with all the different libraries that we have. So HotSpot, or C2, which is the name of the sort of full compiler, was written in C++. Okay, so the majority of the application, the emitter, is in C++. Now, there's been some challenges with C++, not necessarily as a language in its own right, but in particular, the way that it's being used within the HotSpot code. Okay, so what does that look like? Well, one of the main challenges with C++ is it's not a safe language. Okay, and modern C++ has lots of idioms that you can apply, which make it perfectly safe to use. But you have to remember the HotSpot code base is kind of approaching 20 years old, so it's a fairly long-running project. And the idea is that if you've got pointers that represent ordinary objects or ordinary object pointers, if you accidentally dereference a pointer, and an ordinary object pointer is managed by the garbage collector, you'll get a segmentation fault. Okay, I don't know how many people in here have seen a segmentation fault in the JVM. Quite a reasonable number. I haven't seen many of those recently, I have to say. It's kind of going back to maybe 10 or 15 years ago where you used to get those all the time. Maybe I just got lucky, I don't know. It's also legacy, that terrible word, but it's where a lot of smart things have been done. And the idea is that there's a custom malloc that was written inside the JVM as well, so custom memory allocation, custom memory management that works with kind of the Java itself now. And also the tooling, although it's getting better, some of the stuff that you might want to do while you're interrogating the compiler is not necessarily there. And it becomes difficult to make changes. Now, one of the things I kind of find, and this is where we're kind of at the tipping point with Java, is that actually going into the C2 compiler and C++ and trying to get performance optimizations is getting more tricky. And it's not necessarily getting more tricky for Java, which is what it was designed to do, by the way. It's getting more tricky for all the dynamic languages that run on the JVM as well, that don't do some of kind of the tricks that Java has built up over the years. Things like boxing is a good example. So what you end up with is in the situation where it's going to be quite tricky to move the C2 compiler forward in a way that's kind of going to be advantageous for other languages. I have to say, like, all this stuff is experimental. A lot of what I'm going to talk to you about is still experimental, but it's pretty cool, and I think it shows quite a lot of promise. I also find this kind of interesting because looking back at why people would have moved to Java 20 years ago to kind of avoid some of these issues is exactly the same thing that we're doing with Java itself right now in the JVM. Is we're looking at this and going, well, these problems that exist is potentially a good reason for us to move forward. So yeah, I mean, it's been built upon over 20 years. I think there's an enormous number of engineering time that's gone into HotSpot, and it's got us a really long way along our story. But the thing is Java now fast enough to be a compiler in its own right? So could we actually write a compiler in Java? And that's kind of where this talk is going. But one of the problems is that this piece, this JIT compiler is baked into the JVM, or at least it was previously. So how are we going to plug in a different type of compiler? And this is where something called the JVM Compiler Interface, or JVMCI, which is a JET from Java 9, has introduced the ability to actually replace the compiler in the running JVM. Okay? So there are some security things around that modules helps us to resolve. But effectively, what we can do is we can edit, the compiler and actually add in something a little bit different. So that's going to be something we're going to take a look at. So what do you need from the JVM compiler interface? Well, you need to have an idea of what structures it's going to need. So it's going to need to know basically things from that class file, things like the fields and the methods and all the other kind of like structure of the code itself. But in addition to that, you need to know the profile information. Because remember, it's going to need to make decisions based on the running application. You also need a mechanism to then install that compiled code that gets emitted. So the idea of being able to store into the code cache. And along with any metadata that's required for GC and de-optimization. So again, GC is a big part of the Java subsystem. So it produces machine code at a method level, and that's basically what a JIT compiler does. Everything is done on a method level. Okay, so the idea is you take one method, you go off and do some things with what's called the C of nodes, and you get back something that's like the best compiled code you could have for that current running profile of the application. And it uses JET 261. This is the modules JET to actually help protect and isolate some of the implementation, specifically with the one that Graal uses. So we've got this mechanism then that we can now go and start to potentially play around with a different type of compiler within the JVM. So Graal is a JIT compiler. Okay, it has a series of simple inputs, and we're going to look at some of these now. So it looks at the method to compile, and it converts the bytecode to assembly, so that's one piece. It gets a graph of the nodes. So one of the important things that we see during all of the compilation process is actually looking at the actual graph that is created, and that kind of comes from the profile itself. We'll see that as we step through some of the compilation phases, your tree changes as you go along, or your graph changes as you go along. And that kind of is a process by which you're effectively shaking through the different optimizations how your final code is going to look. So you go through a process of taking the initially parsed graph, and you do lots of different steps to it, and you end up with a graph that's then your optimizations all applied. And then you take that and you emit that into effectively what's called the back-end compilation process, which if you remember, Java's got two types of compilation that it's doing. It's kind of doing the compilation with the bytecode instructions to do the optimizations, but then if you're running on Mac versus Windows, there's a different type of assembly that gets chucked out of the back. So actually, implementing JIT in Java is quite compelling. So you start to get language level safety in your expressions, which is cool. And it actually is easy to debug. I've spent a lot of this week just debugging through Graal to just figure out, trying to figure out what's going on in some of the different phases, where I think previously, like I mentioned, I've done some C++ before, but I'm particularly rusty at C++. But if I go and look at some of the Java code and run through the debugger, I can start to see some of the things that are going on without necessarily being an expert in compilers. And it's got good IDE support. So all of the stuff I'm going to do today will be in IntelliJ. So getting started with Graal, I'm actually writing a blog post at the moment because Chris Seaton wrote an excellent post about getting started with Graal and using it to play around with the JIT. Things have actually moved on a little bit now, so there's actually a slightly easier way of doing things. So I'll be posting that online. I'll probably write it on the flight on the way back. So maybe early next week, we'll say. And there's a tool called MX. So MX is it's a series of Python scripts that make it quite easy to work with Graal and work with Graal, the Graal project. So in order to make this work, I've pulled in the code for the Graal compiler. So you go to the Graal project, which is just on GitHub, and you do git pull. I wouldn't advise trying to do that on a train, which is not so successful, because it's quite a big project and there's lots of commits. And the thing that we really care about is the Graal compiler part of the project, which is where all of the nice compiler parts are that will get run and that will step through. So you can run MX build, and that's locally going to build you a version of your compiler. And you can use MX IDE in it to get your IDEs all up and working, so you can do things like remote debugging. And then you can run this MX-DVM. Now this is kind of cool, because what this is doing is it's basically going to install any changes that we make into the compiler, and it's going to unlock a series of options. So the options that I'm going to use, experimental VM options, remember this is still experimental, we're going to enable the JVM Compiler Interface, and we're going to use the JVMCI compiler, so that's the Graal compiler essentially. And then we're going to use compile only. Now the reason I'm doing compile only is to try and make this demo a little bit more simple. If you turn compile only off, it gets quite complicated because Graal starts compiling itself. So if you've got a compiler written in Java, it's going to be interpreted to begin with, and then it will start to compile itself as thresholds are met. So you end up with this really weird thing, which is, I don't know, it just feels really odd whenever I think about it, where the compiler is compiling itself in order to make compilation quicker. So I kind of turn those bits off just so we get a nice simple view. And actually with some of the things we'll look at, it would the inlining that we'll look at would potentially go on a lot further if we weren't stopping at that particular limit. We're going to use something called Graal Done, and that's so we can use some of the inspection tools. And actually, I've got to fix this slightly. We're going to pipe all of the errors out to dev null, which is a bad practice in general, but I don't want you to have to look at hello world printing out a million times. So that's why we're just getting rid of that. And hopefully I don't make any errors, because otherwise I'll get swallowed and hidden away. So there's a tool called Ideal Graph Visualizer that we're going to play around with. And what that does is it allows you to view the tree, the graph as it changes. So we'll actually look at the graph as we go through some of the different phases and have a little idea of what's going on. And the example that we're going to explore, so I'm going to go into one example in detail, and then we're going to kind of, just to kind of like, so we're not here all night, we'll kind of come back up and we'll go over some of the high level examples, and we'll talk about the phases and you kind of see, hopefully get an idea of what this is all about. So inlining is kind of an interesting topic to look at, because I think if you've done any C++, you probably come across the inline keyword. The interesting thing about inline in C++ is most of the time it ignores you, unless they're on the class, small class level methods. It will kind of go, well, the compiler will decide when that's relevant, and it will necessarily not take the hint. But with Java, inlining is different, because inlining is based on that runtime profile. So it knows how you are currently using your methods, and will look to inline them accordingly. So what happens then in general is, this is a picture of our stack on the right hand side. We've got a stack frame pointer, we've got our locals, return addresses and parameters, and when we invoke printline, what happens is the frame pointer moves up, so we allocate a new stack frame, we have to add all the return variables and locals in there, and then when we invoke printline, we do the same again. So you end up with increasing the size of your stack essentially. And then as you come back out of those methods, you have to remove those off the stack, and then eventually you're back to where you started. So that can be quite a lot of unnecessary invokes if your application is always doing the same thing with those methods. So the idea with inlining is that at runtime, Java can decide that when it does the compilation phase to pull all of the outputted code together for that. So it ends up just being one linearly executed function essentially. So that's one of the things, that's basically what inlining does. And we'll try and see if we can get an insight into how that works inside the compiler. So this is my second live demo where we'll actually go in and we'll make a couple of changes as well along the way to the compiler. Nothing dramatic, we'll just print out a few things and we'll kind of see that process working. Cool. So what I'm going to do is I'm going to start up, so I've already built this, but we'll build it again later just to save a bit of time. And I basically got that exact same command that was more nicely formatted on the slides, and I put it into here. So when I execute this, I've got my mind out. It's just picked up actually that earlier on I changed this. Probably should have run it before I did the demo to just save a bit of time. But what it's done is it's actually picked up that there's a new version of the JIT compiler, and it's now installing that into the VM so that I can, so that it uses this version. So what I'm waiting to see now is, basically I'll get there we go, just on time, listening for debug. So it's waiting for my IDE to connect. Okay. Now I've got a couple of breakpoints that I've set in advance. That's mainly so I don't go flying off over something that's interesting. But we'll start up the debugger. And the first thing that we get to is the HotSpot Graal Compiler. Okay, so the HotSpot Graal Compiler it's in here. We'll just add something into this as well, just so we can see what's going on. So we'll add something like system out, print line, request, get method, so we know what's actually trying to be compiled here. We can add in some debug information as well, I suppose, so it doesn't just so we can tell what's ours. So trying to compile request or get method, that's all cool, and we'll step into the compilation process. So we'll go out of here. It's probably going to complain now because I've changed this and not recompiled it, but we'll see if it does that. So it's actually going to compile the method. So this is kind of like where we now start stepping into the compilation process, and we'll see if we can jump into something a little bit different. So okay, so we've got essentially you get a lot of wrapping that happens. It's basically passing in some of the information to the compilation. You can see here that what we've got on the top right there is we're about to compile the print int function, which is the one that we saw before. So we'll step into that. We'll step into perform compile, and then we get this idea of this HotSpot compilation request result. So that's the wrapper essentially that will happen on the result. It does a couple of things and checks to see whether this is on-stack replacement. So on-stack replacement is another really cool feature in the Java compiler, where Java can recognize the fact that it's executing within a loop. And if it knows it's executing within a loop, it can actually compile the loop and then replace the interpreted code at runtime as well. So it's able to, because if you think about it, most Java applications are probably running in some kind of loop. So if the loop itself was still interpreted, you'd end up with your code would still be slow. So that's kind of another nice thing. There's a couple of other things that happen, and then finally we go and we say compile, given the method, given this entry condition. We use the profiling information here as well, and we pass that through essentially to the next stage. Okay, so we've gone back to the HotSpot Graal Compiler, which I think is off by one line at this stage, mainly because I've added that print line notoriously. I'm not going to do that again. What I've just done here then is I've created my graph. So I've got this idea of a structured graph which represents what I'm currently trying to essentially compile. Okay, so we will skip on slightly to this part. So this has gone into the Graal compiler itself. Okay, so we've gone out of the HotSpot compiler now, which is the facade that we've got in place for Java, and we've gone into the actual phase now where it's going to do a couple of things. So I mentioned that the compilation process is essentially two steps. This idea that you've got the front-end compiler, which is the Java part, and then the back-end compiler, which is all about what's the target for the platform that you're currently running on. So we can take a jump into here, and we can actually go down a little bit to actually take a look at the different compilation suites. So as we step through, you can see that we've got a couple of things that get applied. And then down here, we go and see what the high tier looks like. So the high tier context is effectively inside the suites for compilation, we've got high, mid, and low tiers. So the very highest tier is kind of all the things that we would know about or probably have seen or heard of when we looked at compilation before. Things like inlining. So if we were to expand out this slightly and look at the phases in there, you'll see that you've got the canonicalizer phase, which kind of just shapes the tree into something that's standard. And then underneath you've got the inlining phase there. So that's the phase that we'll be exploring, and I've got another debug that will jump us to that. The other thing that you've got in here is things like dead code elimination, and I have a slide that I'll kind of just show you all of the different phases that happen through compilation. But then when you get down to the low tier, it's all like all the really cool stuff like aligning up the memory so it's all padded so you don't get like false read and writes. So that kind of gets quite interesting as well. So if we jump out a little bit into inlining, so we've gone now straight into the inlining phase, we can see what actually goes on within the inlining function. So the inlining function itself then is going to grab hold of some data, and what it basically does is while you've got this idea of unprocessed graph, so while it can kind of go forward, it moves forward through the graph and it tries to figure out where the invocations are and whether it can actually inline those back up. So there's kind of like a step-by-step process that goes through and says, okay, is it worth inlining this, yes or no? And it makes those decisions as we go along. So we can have a look in the move forward function, and you can see that it's got like this idea of what's the current invocation. It takes a look here to see if it needs to do any backtracking and checks it's worth inlining. And then you go through step by step and actually backtracks false. So we go into processing the next invoke, and that's where things get kind of interesting. So I've got here another system.out.println that I'm going to enable, and that's going to basically tell you what it's processing and what info it's found. So what info is it found about actually doing and performing the inline. And if it finds information, then what it's going to kind of calculate is whether it should look and go and do that inline as it goes through the process. So I think what we'll do there then, I'll just check I haven't missed one of my comments that I wanted to put in. Yeah, I wanted to just make this one obvious as well, which is where it's actually making the inlining decision. So it'll decide whether something should be inline yes or no. So I'm just going to put that in there just so you can see when it triggers the actual inline itself. So what we'll do, we'll cancel this and we'll go back out, and we'll just to make it a little bit clearer, we'll rebuild the actual Graal compiler. Okay, that looks like an error, it's not. What it's doing is it's going, hey, I don't need to know about JDK 15 and all those other pieces. And then what will happen is then you see that this will, it rebuilds all of that, the JIT compiler, and then we'll be able to plug that back in. So well, I don't know if I saw a hand at the back, was there a question there? Yeah, sure.
Just see what I'm trying to build this so often, IntelliJ can like print stuff when you hit breakpoints.
Okay, so cool. So an IntelliJ hint. I think one of the things that I found whilst playing around with this is to actually get that to get the code to compile into Graal using the MX tool. Is that you effectively have to rebuild it. So it rebuilds inside IntelliJ, but it's not dynamically kind of rebuilding against the GraalVM. That may well be something to do with how I'm playing around with this, to be honest. Cool. So hopefully in a second we'll be back up and running with our new version with the print lines installed into the running JVM, which I'm not sure how that would kind of flow with the way that we've got this running. So again, we'll kind of go through here, it'll sort of give us this output that it's got the Graal jar that it's reinstalling into the JVM that's executing. So that piece is all nicely done for us, just by figuring out that it's older than it was 7 minutes ago. It's a good point for me remembering how long I've been talking about this. And okay, so it's listening for debug information, listening for the debugger again. So what we'll do is we'll fire this up. We'll actually probably maybe we'll just take a look at the output just to kind of save a little bit of time. And you can see here then that what we've got like coming out of here is we've got hello printing invoking print string print line. It had no information there to really consider whether it should inline that. And eventually we get to the point where it goes, okay, well actually I'm going to process probably inlining print in and print string is not as much value as inlining it straight into main. So you kind of go through this process of going, well, printing, yeah, I could inline that, but actually it's going to give me more bang for my buck if I inline it in main. So the final decision that you get is the inline decision. So you effectively roll that up and you execute it there. So it's kind of nice that you can go in and explore those phases, and it's really dynamic in terms of what you can play around with. Now, can you add in your own phases and plug in other things as custom? Absolutely. You can pretty much do all that within the build tool and within the build chain. Okay, so I just wanted to give you an idea of what the different phases look like and what the different tiers look like. So I mentioned that we've got this high tier, this mid tier, and this low tier. I just wanted to point out that we've got like inlining, that's what we looked at just in a little bit of detail. We're going to talk about things like dead code elimination, loop unrolling, and escape analysis. And then you've got some other phases as well that kind of come back through. So it's kind of interesting that the dead code elimination phase gets applied at multiple different points, because as you optimize and start shaking out your graph, then you'll see at different points where actually it might be worth just eliminating some more of that code. One thing I didn't show you is the IG tool, which behind the scenes was capturing the different trees. So you can see that basically after parsing, this is what the tree looked like essentially from main through to the different method invocations that you got. And you can actually go then and say, well, actually, what happened at the high tier phase? So what did you actually do as the high tier phase in main? Probably the printing one's a little bit easier to see just because there's less going on in that one. So you can see that you've got the error getting pulled in, the invoker link, and the prints that are kind of all going through. There's some guards in there as well that kind of help it. And then down in the low tier, you can see that once it had shaped the tree and applied all the optimizations, the tree starts to get a little bit simpler. So a little bit simpler without going into too much detail. But this is kind of like, again, those tools that when you're working on the compiler, you can use to kind of start to see what effects that you're having with each phase as you go through. Okay, so that's kind of like the tiers and the phases, and that's kind of how all the compiler gets plugged together. Once it's done all the graph shaking, it outputs the bytecode. So I wanted to talk about some of the other optimizations that are in the JVM. So there's this idea of dead code elimination. It's kind of different to the dead code elimination that you'd have within your IDE, where you'd go, okay, you never use that thing down there. Because actually dead code elimination in Java at runtime is, well, maybe you've got an example would be some database object that takes in the constructor, whether it's, I don't know, say MongoDB or some Sybase type thing, so it could make that decision. And if you're using MongoDB, you don't need to retain all that other code, it's just no point. So it will get pruned and thrown away, it's dead code. And as you start to go through and do some of the other optimizations where you start relaying out the tree, the graph, there'll be other scenarios where there's dead code that you can eliminate as well. So dead code elimination is pretty cool. It gets determined at runtime and it gets processed through to simplify the code that you're about to compile. And the size of the code cache isn't infinite, so the smaller things that you have, the better in terms of execution. Now loop unrolling is kind of interesting. So loop unrolling, if you think about when we saw our loop earlier where you've got the goto, you've got the increment, you've got all those different things that you need for iteration. And if you've got a loop that's based on an int, a char, or a short, then those loops can actually be fully unrolled. So if you get to the point where the loop is, say, I don't know, say 100 iterations and you're doing similar things, you can just actually put those 100 iterations in without using the loop. So you actually unroll and just create all the bytecode that way. And then you can potentially go in and do some other things where you hoist things out where you've got duplicate expressions that are getting calculated. And that's part of what the JVM does. It can remove like the need for save point checks, which is when the JVM kind of has a little look to see whether it can do stuff by GC, and it removes the work needed by each iteration. Now, the first time somebody told me about this, I was kind of like, yeah, big deal. Like loops can get enrolled. It's not so maybe not so interesting. But I was having lunch with Chris Newland while we were writing optimizing Java, and I said to him, well, what's the big deal about this loop unrolling? And he was saying that he has a tool called JIT Watch, which allows you to look at like the bytecode and assembly that's coming out of Java from like a top level. And he was saying, well, actually, we had this person who came to us using JIT Watch that had a ray tracing algorithm, so a double nested for loop, and it was unrolling both of those for loops into just one massive, effectively linear ray tracing algorithm. So there's some quite interesting things loop unrolling can actually get to. To give you an example, there's a benchmark here. There's one that uses what's called an int, so a standard int loop, and there's one that uses a long. So this benchmark has been written in JMH. So if you're ever going to write any kind of micro benchmarks, you should always use something like JMH, and that's a whole different talk in its own right. So on the int stride, the throughput is 2,423 operations per second, so that's from loop unrolling, whereas the long stride is actually it's nearly 1,000 operations less per second. So you actually, that's the kind of sort of performance speed up you can get from having probably what you'd be doing anyway, but this idea of loop unrolling is pretty neat. Cool. So in Java 6, I think it was my version 24, like all those years ago, they added something called escape analysis. And this is always my favorite interview question. When you ask a Java developer, when you sort of create an object, where does it get created? Is it on the stack or on the heap? And of course, like any good answer to an interview question, it should always be, well, it depends. And that's true. In terms of what happens, and there's a huge amount of performance improvement related to this. If you've got an object that's it has to be small, it can't be a huge object, but if you've got a small object that never leaves a particular scope, then what you can do is you can actually allocate that object onto the stack, which means that you don't put pressure on the garbage collector. So it's kind of an interesting one. So in C++, this would be referred to as automatic memory management, essentially. So you're not kind of doing anything in terms of creating something on the heap. You create it on the stack. And what that actually does is it reduces the pressure on the GC subsystem. So one of the things that happens in GC, and you've probably seen this when you've looked at GC profiles, is you get a nice sawtooth pattern that looks on your GC graphs where you've got something which is referred to as, well, usually informally referred to as high infant mortality, which means that like out of all the objects that you create, most of them are not going to live for a long amount of time. And they're going to be immediately collected in Eden. And that's actually a healthy thing within Java. But if you can avoid putting them into Eden in the first place, using something like escape analysis, well, you don't need to collect them. So this is kind of an interesting thing. Again, it's like the impact it had on Java was pretty huge. Like when they turned this on later, like a lot of applications saw 30 to 40% improvements overnight. Now this is a good pub quiz one as well. Monomorphic Dispatch. If you've ever worked with something like C++, you've got this idea of static and dynamic binding. So the idea is that if you're not using inheritance, you know exactly where the function is that you're going to execute. You know its memory address. So to execute code in there, it's just a one-to-one lookup. As soon as you introduce something, as soon as you introduce like the virtual keyword for dynamic binding, what happens is you create an intermediate data structure called a vtable. Okay, now the vtable itself, it depends how deep your inheritance hierarchy is, but if you think about Java, that's usually a couple of objects. If you think about some of the old versions of Spring, that'd be like 50 objects, kind of thing. And the idea is that if you're looking for a method, you have to traverse the different vtables that you've got to find where the implementation is. And that's how method overriding works. If you create one with the same name, when you traverse through the vtable, you'll find it before you find the other one. So what that means is, because in Java, every single lookup is virtual, you are paying the cost of indirection over and over again. And pointer indirection is vastly difficult to predict. Okay? So what Java does is the first time you make that call, it observes the path, and if it can determine that it's monomorphically dispatched, that means it's just always going to be that same call site, it applies the optimization for you. Now that was kind of a cool thing because, again, it goes back to, if you can do that, then you end up in a position where you've got this like kind of, you're always OO because you're using Java, but you can kind of solve the problem by some of the smart technology, which is sort of optimizing the vtable. You have to be careful though, because if you load a new class into your hierarchy, you can invalidate like the vtable structure, and then in that case you have to revert the optimization, otherwise you'll potentially be doing the wrong thing. So that's kind of like just a brief sample. You kind of saw that slide. There are so many optimizations that get applied inside the JVM. But the final thing that gets emitted is into the code cache. And I just put this dotted line here because if it needs to back out, it can back out. But there's a new thing. There's a new thing in Java. There's almost a new thing in Java. And it comes up on my slide and it surprises me almost. The code cache has got this new idea. Well, actually, wouldn't it be great if you could extend the code cache to put in basically pre-compiled code? So what they've done is they've added a tool called Java Ahead of Time Compiler, so JAOTC. That's the command line that you can run. And what you can do is you can use that to basically build some of the machine code up front and apply it to the JVM. Okay? Now this is really interesting because I've kind of been telling you this story that the JVM is really dynamic, and this idea that it takes all of the instructions at runtime and compiles them. But some of those things that you do at startup, maybe there is benefit to compiling them up front because then you get quicker startup times. And if you want quick startup times, for example, if you're running on a container on cloud, that can be advantageous. So I'm going to show you what that looks like. Yeah, question?
How does that work with security of the JVM and the bytecode analyzer and so forth? Would that allow you to basically bundle arbitrary machine code into your application?
So the question is well, what would happen with, is that a security issue is essentially what we're looking at. I guess it kind of depends how you load in the ahead of time compiled code. But there is actually something, let me come back, can I come back to that question in a second? Because there's something that happens that I think will stop that from happening, right? And it's a really good question, I've only just answered it myself. So let me show you one other thing. So you're using this tool called Java Ahead of Time Compilation, and you use Graal to build like a shared object ahead of time. Now, it's kind of like an extension to the code cache. And going back to your question, the way that it works is if you've got an interpreted method, when you load that into the JVM, it's got a fingerprint associated with it. And the pre-compiled code that you created ahead of time also has a fingerprint associated with it. So they have to match one-to-one, and it's based on like the content of the files. Otherwise, you can't load that ahead of time compiled thing. And actually, that gets quite interesting because you'll see here that you can use JOTC, create a shared object, but there are lots of other things that you have to do. So you have to tell it what GC you're using, for example. So if you're using parallel GC, you would compile the code in a different way to if you weren't. So there's lots of actual kind of it's really nice, but there's a few things that you have to be aware of. And then when you actually apply it, it's an experimental feature again, but you use the ahead of time library and you load in the shared object. And it has, like you say, that security feature has to match one-to-one. Now the interesting thing about this, and this kind of goes all the way back to the beginning of the talk, where I told you that I liked hacking on Maven. So the first thing I was thinking, this is really cool, like this could actually have so much performance improvements. How do people do it? Because as soon as you change minor version of the JVM, you need to recompile all your shared objects. As soon as you change like the way in which you're going to run your application, you need to compile all your shared objects. You go and have a look at Maven, and there's no support for it yet. So the build tools haven't actually got support yet for the ahead of time compiler, at least from what my research has shown me over the last few weeks. So what I'm actually building now is the ahead of time compiler plugin for Maven. Now that's kind of like an idea. We'll see how it goes, but that could be quite cool because then you can recreate some of these things. Now I've kind of given an example here where I'm compiling Hello World up front, but you can also compile some of the module system. So for example, Java Base. You could compile that module and use that within your application to boost the startup time effectively without kind of wasting time on the JIT, which can then sort of focus on your current profile of your running application. Now I tried to do a little benchmark, but it turned out to be so close and such a bad benchmark basically. I decided not to show it, but the idea is that the timing is actually not a million miles apart. If you want to know something else that's really cool that's happening with JIT that's not inside Graal, there's another project called OpenJ9, which is the Eclipse JVM, which you've probably sort of already seen. But they've got this new idea where you can run something called JIT as a service. So the idea is that you've got all your containers running in cloud, and you've got one container that's basically JIT. So when you hit compile, I don't know if you've seen this before, and I should have probably mentioned it. Compilation is an asynchronous process, so you put it on a compilation queue, it gets queued up, and then it gets converted and sent back. So what they're doing with these sort of clusters of JVMs is they're outsourcing the JIT compilation to another component. It does the compilation, and then if someone else asks for it, it goes, yeah, there's the compiled code. So there's some really fun things that are happening. I actually think that previously we were kind of mostly OpenJDK, Oracle, like JDK builds. The different variants and the different things that are actually coming out now is super interesting. And where we used to, like maybe 10, 15 years ago, have like free JVMs that were all competing, I think we're starting to see that again. And that's really cool for innovation, and it's really cool for our industry as well. Yeah, question here.
Quick question. How's the output?
Right here.
Oh, so there's a, I think.
I was going to ask, how's the output here different from the class data sharing itself? Because they can also output pre-compiled bytecodes, right?
From the class data sharing?
Yeah, CDS.
I haven't seen that, to be honest. All I've seen is this output and compared it, really, to be honest. So I can't give you a direct comparison. In fact, if I'm honest with you, I made that slide 2 days ago. I found out that was looking into this, and in terms of how new it is compared to some of the JIT compilation stuff that we've been using for years. So yeah, I think the jury's still out, and I'm hoping that what I can do is actually, once I've created some stuff in Maven, where I can start to build like reproducible subsections of the JVM, we'll be able to start doing some benchmarking against how much performance you do get. I haven't actually seen, it's something actually, I'll have a look and I'll put it on Twitter. I'd be quite interested just to see if there is any kind of like general performance things on this. I haven't got that far yet with my own personal research, but if you find out, let me know. It does sound pretty interesting. Okay, yeah. Cool. Sorry, that's a bit of a cop-out answer, but I don't want to tell you, don't want to spin you a yarn. Okay, so there is a bigger picture here. Now, most of the time, and kind of hopefully one of the reasons that you're here is just kind of out of intrigue about what's happening in the ecosystem. You're not usually going to be down looking at what the JIT compiler is doing. Right? That's not what most Java developers spend their days on, because that's not really what the JVM was designed for in some ways. It's designed to simplify that. You would be potentially looking at this though if you're doing some high performance in Java, if you're really caring about that mechanical sympathy aspect of your application. And there are some companies within our industry that are building things like trading systems, etc., based on Java. But there's the thing that's going to hit you the most is probably garbage collection. So there's still issues here potentially around GC that would, you might be better, if you're looking to optimize your application, time might be better spent looking at things like GC. It's probably better spent looking at things like databases, networks, and any I/O-bound operation. That's usually where you spend a lot of time. And certainly from some of the stuff that we've been doing on API gateways, we've been comparing different web server technologies. So looking at something like, for example, Jetty versus things like the more reactive features in things like Spring Cloud Gateway and the React project, and looking at how they differ with their non-blocking NIO. And then all of a sudden you see like the vast differences in scale that you can solve by changing that technology. It makes this stuff kind of pale into comparison a little bit, but still, as I say, it's really interesting. And that kind of encompasses everything. And sometimes your optimization is not necessarily for speed. A lot of things that we're talking about now is moving things onto cloud, especially some of the stuff that I work on. And actually having to have, for example, at startup, where I don't know if you've ever seen the profile of the JVM on start, but you kind of go really high in terms of memory usage, you drop down somewhere in the middle, and then you kind of sit around there. But normally at that startup, you have to allocate all that memory to say, well, I'm going to have all this space reserved so I can do that startup time, memory allocation. But if you can take some of that and put it into a shared object, then you won't have that spike anymore. So actually you can half your container size and half your cost of your cloud plan, in theory. So that's kind of a cool thing, so optimizing for a different thing. So in terms of that's pretty much the end of the talk. I'd just like to acknowledge a few people. Chris Seaton had a really excellent blog post that got me started on some of the things that I ended up looking at. Ben Evans has helped me review stuff, and has been a long-standing friend. And actually, I think Ben started teaching me this stuff in 2008 when he said it was at one of the London Java Community Conferences. He goes, "You know how the JVM works, don't you, Jim?" It's like, maybe a little bit. Anna Evans, Ben's wife, did some of the amazing slides that we have in here as well. And Martin Verberg in terms of his encouragement. The GraalVM and OpenJDK teams are pretty cool. The projects are really interesting. Alex Blewett gave me an excellent review of my talk, and if Alex is watching the video, sorry, I still have some of your feedback to apply. And then also just again, thank you once more to the NYJavaSIG for setting this up at such short notice. Talking about Twitter handles, I'll add that onto the slide as well and see if I can plug you for some more votes at KubeCon. Thanks for listening, guys. Yeah, I'm happy to take any questions.
If you just raise your hands, I'll pass the mic around.
Hi, so, turn it on. Testing.
Should be on.
I don't think it's on. But I can talk further about it.
I think we got here.
Okay, cool, yeah. So, I know there's some performance penalties for calling native code, like from the JIT interface. Those same restrictions apply when you're calling ahead of time compilated code from what you're showing?
So the question is calling JIT code, there's some performance hits versus potentially like stuff in the AOT libraries. I think the one thing I would say, and it kind of again goes more towards the areas I know and I've looked at, a lot of those phases that you kind of saw there that are applied at runtime are all based upon the profiled information of the application that's running. And in many cases, like the JVM for, I say the last 10 years, 15 years, has not used any ahead of time compilation, and it's been able to, in general, I'm not saying in all cases, because that wouldn't be accurate, but in general, the output of the performance is all being kind of, the improvements that we've got over some of the languages more statically compiled like C++, is purely due to the fact that we've been able to observe the profile and to kind of start to do things to the graph that you can't necessarily see with statically compiled code. So with your AOT code, you're going to get those same restrictions that you won't know how it's going to be used within the context. So a good example is if you compile Java base, you don't know how things like your some of the stuff that's in there is going to be inlined into your functions potentially, and you're missing out on that opportunity to be able to do that. In terms of like versus the JNI interface, again, I've not seen any like specific performance like measurements, although it's quite an interesting. It would be interesting to do that comparison. Sorry.
The question I have was, you talked about loading precompiled code from shared objects. How does it compare to JVM like Zinc, which uses a ready now feature where it saves, I believe it saves the compiled code in a file and then reloads it when it restarts the next time?
Okay, so the question is how does I'm going to say I probably don't know the answer to this up front. The question is how does it differ from compiling your code in a way that was based on a previous iteration, like versus something like sort of the ahead of time compiler, right? So I think that there's a real danger in doing that, in actually kind of like having code that's pre-compiled based on a previous run. It also kind of comes in as well, like some companies pre-warn their JVMs before they put them into rotation with what they have as predicted traffic patterns. I was talking to Kirk Pepperdine about this a little bit at Devox a couple of years back, and he was saying a lot of problems that he's seen within different companies has been down to attempting to model the same profile of application over and over again. Because I think the problem is that once you go beneath a certain level in terms of like into some of the JVM internals or some of the internal libraries, you don't necessarily know like, if they would inline in the same way the next time round. And I actually think this is the same thing applies. Like, I think it can back out of some of the ahead of time compilation decisions. But again, as of the comparative performance, I couldn't tell you that at the moment. Yeah, question there.
So considering applications where sheer speed of execution matters and we're not bound by I/O or network or database, what types of applications would indicate that they're going to run faster on modern Java JVM, and what types of applications would run faster on a traditionally compiled language like C++ or Fortran?
Okay, that's an excellent question, and there's so many caveats to that question and different types of answers. So I'm going to go through a couple of them, and we probably have to extend some of this into a bar because they kind of get kind of interesting.
We've got plenty of bars.
Absolutely. There is one key difference. So Java can emit bytecode instructions, machine instructions that are very close to C++, but there are a couple of places where we still don't quite do as well as C++. And there are some changes coming in Java, I think, that are going to help us with this. But I'm going to speak without my Java 14 hat on for a second, mainly because I haven't had time to read much about it. So when it comes to actually storing arrays of objects, which you do quite frequently, even if you don't realize it, storing arrays of objects ends up being an array of pointers. Okay? So when it comes to vectors in C++ and you store an array of objects, you are storing in laid out in memory objects that are side by side, that then when you process through them, you get all the benefits of things like look ahead, pre-caching the cache lines as well, and then your execution performance goes up just due to like principle of locality in terms of like how you traverse the data structures. That is something that we still, in Java, by kind of default mechanisms, don't manage to reach the same performance as that. So there are certain things in that area where, and because that's so common across the application, that you'll see that can really kind of hurt us in terms of what we can do. So in terms of like where are we going with that, there's a couple of projects that were proposed, and kind of like in some of the more productized JVMs that are for sale, you can do stuff like use the object layout features, where you can use something that kind of wraps things like an array into an array-like structure. And if you were compiling that in normal Java, it will still be an array of pointers, but if you put it on a particular VM, it will lay the objects out in memory so they're next to each other. So there are certain things like that where you definitely still get performance. Now, kind of going back to your other thing about like things like where you're looking at C++ versus Java, the thing about C++ is you will always get deterministic performance, okay, within reason, right? So you always get deterministic performance. When it comes to things like Java, you're always going to have overheads that you're kind of potentially going to battle against, but you'll otherwise have to use idioms to get rid of them. So things like, for example, garbage collection. Like if you're wanting to do things that are performant, you need to make sure that your memory allocation rates are below like 1 megabyte a second. If they're not, then you immediately have a problem with garbage collection that's going to hit you when you're doing high performant code. So you end up having to do things like allocating off heap, as an example. And if you're going to do that, and if anybody's doing that at the moment, there are some really cool libraries that are based on a project called Aaron, which is written by Martin Thompson. And if you drop down a level, there's a project called Agrona, which has a bunch of different stuff where when you allocate buffers, for example, you can allocate them off heap. There's other things that you can do there where you have like non-blocking queues and non-blocking queue implementations. So those areas then start to become quite interesting in terms of getting you more towards that performance that you get from something like C++. So it kind of all wraps in, but the biggest question that you have to ask is, whereabouts do you draw that line? Like between what is acceptable performance and what isn't? And if you were Bjarne Stroustrup, you'd probably draw that line further towards C++, then maybe where I would draw that line, which would be further towards the Java side. And it really just depends on the domain in which you operate, is the honest answer. I think when you think about things like the STL in C++ and the way that the language is designed, like performance it's at the heart of everything. It really kind of is in terms of the structures, they go down to a point where you're going to get pretty decent performance even using things in the standard template library. When it comes to Java, it was always designed to be a blue-collar language in terms of simplifying things. And I think when we start talking about things like this, like they're super interesting, and actually the way that people are using this now, you can probably get most of the way towards where you want to be in terms of performance. So I know that was a really waffly answer, but I think there are so many factors into the question that you asked that you almost have to take all of those on one at a time and figure out what it means within your specific kind of like program and application development. That's probably the longest answer to a question I've ever given, sorry about that. And there's still more, there's still more.
Questions?
Yeah.
Going back to your example about loop unrolling, I thought that the performance of integer loop, better performance, had more to do with unwillingness of Java to remove safe call.
Yeah, okay, so
the pages of long loop, more
so
than with the loop unrolling itself.
okay, so the point there that's been made, and I think you're accurate, by the way, is that with the loop unrolling, like one of the biggest advantages is not just necessarily putting the code in line, so it's all executing sequentially, but by removing the loop counters and effectively the back branch with what you've got in place there, that you no longer need some of the save points, which potentially where like, the JVM can pause and do some other pieces along the way. So you're implicitly removing those as part of loop unrolling, which kind of contributes to the overall performance. So I think, yeah, you're right, like the way that you kind of get to that is it's almost like loop unrolling itself is the boost in performance, but then the part of what makes up that boost in performance is some of the things that you've been able to remove as part of that process. That's a really good point.
Another thing also about optimizations. I think I thought that Java could deal with more this is in terms of monomorphic dispatch versus megamorphic dispatch. I thought the JVM could deal with more than one implementation of the interface. It would cache up to 2 implementations, but implementations would be transit to the third one. Then it would fall into a common trap, de-optimizing the method. But that may be wrong. I just wanted to ask you what's your opinion. Because you mentioned there's just one implementation, and if you load another implementation of that class, then the method gets de-optimized. I thought that the virtualization happens with up to 2 implementations of the same class.
That's an interesting point. I'm not sure is the honest answer either. The case that I've seen is mainly around monomorphic dispatch, but I think so. Basically, I was having this conversation with Alex Blewett over email yesterday, and I said I'll have to read up on that over the weekend, and that's something I need to do. So I actually, once again, I think you're. From what I remember reading yesterday, I think you're accurate, but I'd like to come back and confirm that on Twitter or something.
I'm basing this on some Java optimization video courses by O'Reilly, so I'm not sure it may be specific to specific compilers.
If those O'Reilly courses were done by Ben Evans, I would say he's right. And then if they were done by someone else, I'm sure they're right as well. It's just, yeah, I honestly don't know. Yeah?
Earlier you said in JVMCI, all the compilation is done at the method level. Then how do you do inlining? Because that goes across methods.
Right, so the question is that I made a statement that all of the method, basically all the compilation is done at a method level, and the question is like, how does that work across inlining? It's actually at the top level method. So the idea is that if you've got like, for example, in main, and you've got that chain that goes through, then actually the way that the optimization would happen is it would look down the method chain and it would look for opportunities to inline. Now it might not be able to inline everything, okay? So one really good example of where it can't inline is it might go down 5 methods and then suddenly find there's something like a weird exception handler. And they'll go, I can't inline that because of the way the exceptions are handled. It might go a bit further down and find one of those things that you sometimes find in legacy code where there's like 2,000 lines of code inside the method itself. And it'll go, well, actually I can't inline that either. And sometimes people ask, like, what's the best tip in terms of performance? It's usually to write small, well-maintained methods. That's because then inlining has got more opportunity to kick in. But yeah, basically the way that it happens is at the top level, but the invocation chain as it moves forward through, that's when it makes decisions whether to inline those or not into that top level. And you can get a situation where generally you have to be careful because you don't want to inline methods into too many places, because then trying to do like different optimizations ends up in some kind of like de-optimization storm. So you tend to find that methods will only get inlined like up to a limit in certain different places, and then otherwise it will use kind of the non-inline version.
Which profilers, such as mission control, are they keeping up with these advancements, and which one would you say is the most up to date?
In terms of the profilers that you would use in like just sort of look at in production kind of thing, that's a good question. I have to admit, like in terms of profilers, the stuff that we've been doing for profiling recently is mostly based on like what we can scrape from an actuator endpoint, and that's been enough for what we have needed. We haven't necessarily had to go down and look at the sort of like at the JVM level for a while. We used to use some of the JClarity tooling that was around. I think it was just called JClarity to give some of the information. In terms of like other profilers, I think there's quite a lot out there. I think it depends on like what your overhead constraints are in terms of like how you want it to impact or not impact your code. In terms of like are they keeping up, I think they would, just purely because of the fact that the JVM itself isn't changing. Like it's more the subsystem that does the compilation. So in terms of like performance and monitoring like what's going on when the code's actually executing, I think that's going to be roughly the same. Like, I don't think there's too many like drastic changes that would happen. But I'm happy to be called wrong on that. If there's anybody who's got a better example of profilers, for example. Hey.
I have a question. You said something earlier about, you don't really want garbage collection to kick in.
Oh, sorry, if I said that, I didn't mean that.
Well, no, I mean, like, before performing code,
yeah,
right?
Okay, yeah, sure.
When it kicks in, like, and you perform a code, like, it kind of sucks. And obviously you do want to kick in, but in those situations, with a just-in-time compiler, do you think that like objects can be freed if they fall out of scope, like in time, just in time, like it knows that these objects won't be used anymore, they're short-lived, they're not on the stack, they're on the heap.
So what you are, so a couple of things. First is just to clarify my statement.
Yeah.
In general, you actually want GC to be running frequently for short amounts of time. That's a healthy GC pattern.
Yeah.
If you get to the point where you need to have like linear performance or like trying to get to good performance, then you want to have something whereby you limit where GC is done, and you can do that by things like off-heap allocation techniques. To go to your specific question, which is kind of an interesting one, which is when you basically go out of scope of an object, so when it kind of becomes unreachable, like should you perform GC at that time on that particular object? And the honest answer is that gets like really, really difficult to start to think about with a memory managed system like Java. It's being deliberately done to try and make sure that when you kind of like do GCs, the time is limited. And what you're really referring to is it's an idiom in C++ called resource acquisition is initialization. So once you've got nothing left holding onto the resource, then you can basically free that object using like the old freestyle command and pay that there. In terms of like, will that ever happen in Java? I highly doubt it. I think the way in which the GC subsystem works and the way the algorithms that are used against it are all designed around basically having unreachable objects that are analysed through, basically looking at different regions of the heap. And I think that's the trade-off like with the generational garbage collector, because when something goes out of scope, it's very difficult to know if it's actually gone out of scope in terms of what's happening behind that object, what does its references look like, does it have circular references, and all of a sudden you end up basically doing automatic pointer management and you're back to C++. So it's a nice idea, it's not like the wrong way of thinking about it, it's just the wrong language for that idiom, I think. I actually really like C++ as well, by the way, but Java is my favourite. Cool. Thanks very much, everyone. Cheers.